Okay, section 3.2 talks about two different theorems. One is called the Rolle's theorem, and then the mean value theorem. So before we start talking about the two different theorems, we need to review just two quick things. First thing is we need to review where a derivative does not exist. All right, so fill this in as you go along in the video. One place where it wouldn't exist would be where it's discontinuous. So wherever the function is discontinuous, the derivative is not going to exist there. So I would write any discontinuities. If you can read that. Another place would be any sharp corners. So we know like absolute value graph. This point right here, the derivative does not exist. So I'll call that a sharp corner. Another place would be what we call a cusp. An example of a cusp would be, kind of looks like a V, okay, or it might look like this. That would be an example of a cusp right there. Okay, so cusp. And then a vertical tangent. The derivative does not exist there, because the slope of a vertical tangent line would be undefined. Okay, an example of what that would look like. Remember something like that. I have a vertical tangent right here. So those are the four situations where derivative would not exist. And the other thing you need to remember, what is the slope of a horizontal tangent line? Horizontal tangent line, just like if I had this, here would be my horizontal tangent. Horizontal tangents always have a slope of 0. Okay, so those are the four things that you will need to remember for section 3.2. Okay, the first theorem we're going to talk about is Rolle's theorem. Here's what it says. If f of x is continuous on a closed interval AB, and it's differentiable on an open interval AB, and if f of A equals f of B, then there exists at least one number C in that open interval such that f prime of C is 0. So out of all that, what is it saying? It's saying as long as the function is continuous, with no sharp turns or vertical tangents, and as long as f of A equals f of B, then there has to be at least one point where the graph has a horizontal tangent. The last section we talked about extreme value theorem, where you can have maxes and mins on the endpoints sometimes. Well, now we can have maxes and mins in the interior or inside those endpoints. So here's kind of what the Rolle's theorem is saying. If I have this graph, here's some point A and here's some point B. Okay, I'm just gonna draw. This would be. Let me draw the graph in here first. I know that's kind of ugly, but we're going to say that's the graph. Okay, first of all, here's a closed interval from A to B because my points are included. This is a continuous function. And we're going to say this is not a cusp right there. That should be more of a smooth curve. But we're going to say the derivative exists at all these points. So here's what it says. As long as the function is continuous with no sharp turns or vertical tangents, and as long as f of A, so this endpoint, equals this endpoint, then there is at least one place where the graph has a horizontal tangent. So in this one, whoops, I actually have 3 horizontal tangents. One right here, one right here, and one right here. And that makes sense because we learned yesterday that any time I have a horizontal tangent or the slope is 0, I have a critical number there or a local max or an absolute max or min. Here's a min, here's a max, here's a min. Okay, so that's what Rolle's theorem is saying. All right, if f of A is equal to f of B, then I have to have at least one place where I have a horizontal tangent. Okay, same thing if I just had a graph that looked like this. Okay, here's my closed interval. My f of A equals my f of B. Here's my horizontal tangent. Okay, so you have to have 3 conditions in order for Rolle's theorem to be satisfied. Here are the 3 conditions. The function has to be continuous. The function has to be differentiable on that interval, then f of a has to equal f of b. So before you can even use Rolle's theorem, those three things have to apply. And to find the number guaranteed by Rolle's theorem, we're going to find the derivative, set it equal to 0. So what they're going to want you to do today is first say yes to each three of these questions. And after you say yes to those three questions, they want you to find where these horizontal tangents occur. Okay, so let's look at what an example would be. For the function f of x equals 3x squared minus 2x, show that Rolle's theorem is satisfied on the interval from 0 to 2/3 and find the number guaranteed by Rolle's theorem. So, first thing we have to do is answer those three questions. So, is 3x squared minus 2x continuous on this interval? Well, I don't even know what this looks like, but I do know that it's an x squared. X squared is always a parabola. Okay, so I know that all parabolas are continuous. So I'm going to say, yes, it is continuous. My second one, is it differentiable on that interval? I know that there's no breaks in this graph, there's no corners, there's no cusp, there's no vertical tangents. So, yes, it's differentiable on that closed interval from 0 to 2/3. And 3, does f of 0, here are my endpoints, equal f of 2/3? So they're saying if I graphed this, and I'm graphing it on this really small interval, just from 0 to 2/3, do these two endpoints, are they the same? Well, I would have to plug those in and figure it out. So I'm going to plug in f of 0. And if you want to do this on your calculator, that's fine. You would just have to show what that f of 0 and f of 2/3 is equal to. When I plug 0 in, I'm going to get 0. I'm plugging this into my original equation. When I plug 2/3 in, I get 3 times 2/3 squared minus 2 times 2/3. So that's 3 times 4/9. So that's 12/9 minus 4/3. 12/9 can be simplified to 4/3. So I get 0. So does f of 0 equal f of 2/3? Yes, because they're both equal to 0. So this means, since I answered yes to all three of these questions, that Rolle's theorem can be used for this. Now I want to find the number guaranteed by Rolle's theorem. So this is what we're going to do. We're going to find the derivative of this, set it equal to 0 and solve. And that's the number where that horizontal tangent line exists. So f prime of x equals, the derivative of this would be 6x minus 2. Set it equal to 0. If I solve for x, I have 2 equals 6x. Divide by 6, so x equals 1/3. Now, we have to be careful. This number should always fall inside this interval. 1/3 is inside from 0 to 2/3. So if I were to graph this function from 0 to 2/3, I'm going to have a horizontal tangent when x is equal to 1/3. Okay? Let's look at example 2. For the function f of x equals x squared minus 5x plus 4, show that Rolle's theorem is satisfied on the interval from 1 to 4 and find the number guaranteed by Rolle's theorem. So question number 1. Is this function continuous? It's an x squared function, which means it's a parabola. So yes, it's continuous on that interval from 1 to 4. Is it differentiable? I don't have any sharp turns, cusps, vertical tangents, discontinuities. So yes. Does f of 1 equal f of 4? Well, I'm going to have to plug these numbers in and see. So when I plug 1 in, I get 1 minus 5 plus 4, which gives me 0. And it won't always equal 0. Okay, it just so happens example 1 and 2, it did. F of 4, so 4 squared would be 16 minus 5 times 4 is 20 plus 4. And remember, I'm plugging it into this equation. Negative 4 plus 4, 0. So I know that f of 1 does equal f of 4 because they both equal 0. So I know that I can use Rolle's theorem. So Rolle's theorem says I have a number guaranteed to fall between 1 and 4 that I have a horizontal tangent on this curve. So to find that, I'm going to take the derivative, set it equal to 0, and solve. So the derivative would be 2x minus 5, set it equal to 0. So when I add 5 to both sides, divide by 2, so x equals 5 halves, or 2 1/2. So if I were to graph this parabola and just show it from 1 to 4, I'm going to have a horizontal tangent at 5 over 2, which means that's going to be a minimum at 5 halves. Okay, let's look at example 3. Explain why Rolle's theorem does not apply to the function from 0 to 2. Okay, so first of all, let's just kind of look at the graph, what this would look like. This is an absolute value, so I know it's shifted to the right 1. So now my vertex is here. I know here's 1. At 0, I have this point. At 1, at 2, I have this point. So here is the graph of, that should be a straight line there, but you get the idea. Absolute value of x minus 1. There's the graph. That's kind of bother me, but okay. So number 1, the question is this continuous? From 0 to 2. Yes, it's continuous. Question 2 says, is it differentiable from 0 to 2? Well, in this one, I have a problem. I have this sharp turn at 1. Same thing here. I have this sharp turn at 1. So the derivative does not exist where I have a sharp turn. So the reason why I can't use Rolle's theorem would be because the derivative does not exist at x equals 1. All right, so that was Rolle's theorem. This also goes along with Rolle's theorem. Example 4 says find the two x-intercepts of the function and show that f prime of x equals 0 at some point between the two x-intercepts. So this is basically Rolle's theorem again. It's just wording it in a different way. So first of all, I'm going to find the x-intercepts. There's lots of ways you can do this. You can graph this, see where it crosses the x-axis. I can use the quadratic formula. This is easily factored though. I can factor this, set it equal to 0, and solve. I know that x and x go here, my signs are the same, and they're minus. Factors of 2, that when I add them I get 3, 2 and 1. Then I set each factor equal to 0. So x equals 2 and x equals 1. Those are my x-intercepts. So when I graph this, here's 1, here's 2. It's going to look something like this, just a sketch of it. So now, show that f prime of x equals 0 at some point between these 2 points. So remember, here would be my horizontal tangent that we're finding. So I'm going to find the derivative of this. F prime of x equals 2x minus 3. Set it equal to 0. So I have 3 equals 2x. Divide by 2. So x is 3 halves, or 1 1/2. So then that makes sense. If this is 1, this is 2, I have a horizontal tangent at x equals 3 halves. Okay, the second theorem we're going to talk about is the mean value theorem. Okay, here's what the mean value theorem says. If f of x is continuous on a closed interval AB and differentiable on an open interval AB, then there exists at least one number c in the interval such that f prime of c equals f of b minus f of a over b minus a. And this right here is actually your slope formula that you learned in Algebra 1 and Geometry. Okay, so what does this actually mean, this mean value theorem? Here's what it means. As long as the function is continuous, with no sharp turns or vertical tangents, then there's at least one place where the graph has a tangent line that is parallel to the line through the endpoints. So I'm going to draw just a quick little sketch to show you what they're talking about. Okay, if I have a graph, here's point A, here's point B, okay, and here are my 2 points. Here's my graph, okay. Here's what they're saying. I can connect my 2 endpoints with a line, and this would actually be a secant line. Okay, so there's my secant line. All right. It's saying that there's at least one place where the graph has a tangent line that is parallel to the line through the endpoints. So if I draw in a tangent line somewhere on that, the mean value theorem says I have a tangent line that's parallel to this secant line through my endpoints. Okay, and this is the formula that you would use anytime they're talking about the mean value theorem. So what they would want us to do is find what point C that this tangent line occurs. Okay, so let me show you what it looks like as an example. Determine whether the mean value theorem can be applied to f on the closed interval. If the mean value theorem can be applied, find all values of C in the open interval. So again, we have to make sure that it's continuous and it's differentiable on the interval that they gave us. So number 1, is it continuous? Yes, because it's an x squared function. Is it differentiable? Yes, because I don't have any sharp turns, anything like that. Okay, so look back. Is it continuous and if it's differentiable? Those are the 2 things that I have to make sure applies for the mean value theorem. Okay, so now first thing we're going to do is we are going to use this part of the equation. We're going to find f of b minus f of a over b minus a. So that's the first thing I'm going to do. F of b. Now, when they give you an interval, this is always your a, this is your b. So I'm going to find f of 1 minus f of 0 over 1 minus 0. So I'm actually plugging these numbers. I'm going to plug 1 in and see what I get. So I have 1 squared is 1, plus 2, there's 3. 3 minus 1, that's 2. So when I plugged 1 into this equation, I got 2. Now I'm going to plug 0 in. So I have 0, 0. So 2 minus a negative 1 over 1. So my answer is 3. So I did this first part. I actually found the slope of the line. So now I want to find f prime of c. So that means take my equation and find the derivative. So my derivative is 2x plus 2. And I want to know, okay, when is this derivative equal to 3? So I'm plugging 3 in place of my derivative right here. And now I'm going to solve. So when I solve, I'm going to subtract 2 from both sides and get 1 equals 2x. Divide by 2, x equals 1/2. Okay, so that means that at 1/2, x equals 1/2, the slope of that tangent line is going to be 3. Okay, so we have one more example. Okay, determine whether the mean value theorem can be applied. If the mean value theorem can be applied, find all values of c in the open interval such that, and then it gives you this f prime of c equals f of b minus f of a over b minus a. So is this continuous from 1 to 4? Okay, yes, it's continuous. If you're not sure, you can graph it, or I can plug in all my numbers and place this x and make sure I don't ever get undefined in there. And is it differentiable? Yes. All right, so the first thing I'm going to do is find f of 4 minus f of 1 over 4 minus 1. So when I plug 4 in, I get 5 minus 4 over 4. So that's going to be 5 minus 1, which is 4. When I plug 1 in, I get 5 minus 4, which is 1, over 4 minus 1. Okay, so I know the slope of that is going to be 1. Now I'm going to find the derivative of this and set it equal to 1 to find out where that occurs. So I'm going to rewrite this first. I have 5 minus 4 over x, but when I rewrite that, it's 4x to the negative 1. Let me fix that real quick. So 4x to the negative 1. Now I'm going to find the derivative. F prime of x equals derivative of 5 is 0. When I bring this down, I get negative 4 times negative 1 is 4. Subtract 1 from your exponent. So now I found the derivative. I'm going to set that derivative equal to 1. And I'm going to fix my negative exponent. So now I just need to solve for x. When I solve for x, I can multiply both sides by x squared. So I get x squared equals 4. Take the square root, I get x is equal to plus or minus 2. Now, I always have to check because this answer has to fall in my interval that they gave me. My interval is from 1 to 4, so instead of having two answers, I just need the positive 2 as my answer. Okay. All right, your assignment for this section is page 176, 5 and 7, 11 through 23 odd, 33 through 36, and 39 through 47 odd. Okay, you'll have the rest of the hour Tuesday to finish, and then I won't be here on Wednesday, so you're going to finish your homework on 3-1 and 3-2 on Wednesday, and then we're going to have a quiz on Thursday. Okay, that's the end of section 3-2.